Lesson: Theoretical basis of generative vision models. Theoretical basis of generative vision models. Generative vision models have emerged as a cornerstone in the realm of artificial intelligence, offering profound capabilities in understanding and generating visual data. These models are fundamentally grounded in the principles of probability and statistics, where the core idea is to capture the underlying distribution of the data. By doing so, they enable the generation of new data points that are statistically similar to the observed data, thereby providing a powerful tool for numerous applications such as image synthesis, enhancement, and translation. Understanding the theoretical basis of these models is essential for professionals aiming to implement and optimize AI-driven computer vision solutions. At the heart of generative vision models lies the concept of probabilistic modeling. The primary goal is to design models that can learn the probability distribution of a dataset and subsequently generate new samples from this distribution. Variational autoencoders and generative adversarial networks are two prominent frameworks that embody these principles. VAEs, introduced by Kingma and Welling, leverage the variational inference to approximate complex posterior distributions. They employ an encoder-decoder architecture where the encoder maps the input data into a latent space and the decoder reconstructs the data from this space. The KL divergence, a statistical measure, is used to ensure that the learned distribution is close to the true data distribution. GANs, on the other hand, introduced by Goodfellow et al., consist of a generator and a discriminator locked in a minimax game. The generator aims to produce realistic data, whereas the discriminator endeavors to distinguish between real and generated data. This adversarial training paradigm encourages the generator to produce increasingly realistic samples, thus closely approximating the true data distribution. Despite their differences, both VAEs and GANs seek to model the data distribution, albeit through distinct approaches. Implementing these generative models in practice involves several actionable insights and practical tools. TensorFlow and PyTorch are two widely used frameworks that provide comprehensive libraries for building and training VAEs and GANs. These tools offer pre-implemented layers and optimization algorithms, allowing professionals to focus on the architectural and hyperparameter tuning aspects. For example, PyTorch's torch.N module facilitates the creation of complex neural architectures with ease, while TensorFlow's TF gradient tape allows for efficient computation of gradients, essential for the backpropagation process in GANs. One practical challenge in deploying generative models is ensuring stability during training, particularly in GANs. The adversarial nature of GANs often leads to instability, manifesting as mode collapse or non-convergence. To mitigate these issues, several strategies have been proposed. One effective approach is the use of Wasserstein GANs, which replace the traditional binary cross-entropy loss with the Wasserstein distance. This metric provides a smoother gradient flow, enhancing training stability. Implementing WGANs requires modifications in the loss function and the addition of a weight clipping step, both of which are well supported in libraries like PyTorch and TensorFlow. Another critical aspect of generative vision models is their ability to perform conditional generation. Conditional GANs extend the GAN framework by incorporating additional information, such as class labels, into the generation process. This capability is particularly useful in applications like image-to-image translation, where the goal is to transform an input image into a corresponding output image. The Pix-to-Pix framework, built on CGANs, exemplifies this application by enabling tasks such as converting sketches to realistic images or day-to-night transformations. Implementing Pix-to-Pix involves constructing both the generator and discriminator to accept the conditional input, a task simplified by high-level APIs in TensorFlow and PyTorch. Case studies further illustrate the practical impact of generative vision models. In the medical field, VAEs have been utilized to enhance MRI images, improving their quality by learning from high-resolution samples and generating enhanced versions of low-resolution inputs. This application not only aids in accurate diagnosis but also reduces the need for repeated scans, optimizing resource use. Similarly, GANs have been employed in the fashion industry to generate diverse clothing designs, accelerating the design process and enabling rapid prototyping. Despite their strengths, generative models are not without limitations. One significant concern is their interpretability, as the learned latent representations in VAEs and the decision boundary in GANs are often difficult to understand. To address this, researchers have explored disentangled representations, where the latent space is structured such that each dimension corresponds to a distinct interpretable feature. This approach enhances the model's interpretability and facilitates more controllable generation. Implementing disentangled representations involves modifications to the training objective, such as introducing a beta parameter in VAEs, which can be seamlessly integrated using TensorFlow or PyTorch. In conclusion, the theoretical foundation of generative vision models is deeply rooted in probabilistic modeling, enabling these models to synthesize realistic and diverse visual data. Frameworks like VAEs and GANs provide robust methodologies for capturing and generating data distributions, supported by practical tools such as TensorFlow and PyTorch. Addressing real-world challenges, such as training stability and interpretability, requires a combination of theoretical insights and practical implementations, exemplified by strategies like WGANs and disentangled representations. Through case studies and applications, the transformative potential of these models is evident across various domains, highlighting their significance in advancing computer vision technologies. As professionals continue to harness these models, a thorough understanding of their theoretical underpinnings will be crucial in driving innovation and achieving impactful outcomes.